Hi and welcome. In this video we're going to look at how to model the cost of building the Death Star, which is this image right here. Now if you're not familiar with it, the Death Star is a space station, an enormous space station that can float through space and destroy planets in a single shot. Now I came across this great article on incentives.net but that explores this idea, and I just wanted to give a background on some of the calculations so that you can understand just how this is done. How do you model something that seems so impossible? How do you access that through mathematics? Basic idea is there's this enormous station, and right here, this is the weapon right here that usually fires out in the Star Wars movies, and the weapon is able to fire out and destroy our planet in a single shot. So this is a massive and scary and evil idea, and a great one for science fiction. Now, to understand how long it would take to build this thing and how much it would cost, one of the first things I would do is look at the volume of this station. And to do that, we should look at the diameter. And of course, diameter goes right through the center here. And we're going to assume, for all intents and purposes, that the Death Star is spherical, right? There's this little cutout here where the weapon fires from, but we're going to ignore that, right? We're estimating. And this whole process is about estimation. So anyway, the diameter here, what is it? Well, there's of course argument and speculation on this, and it depends which movie you're looking at, but we can assume that the diameter of the station is about 140 kilometers. So that's our first observation. The diameter is about 140 kilometers. Now to find the volume of a sphere, because we're assuming that this is sphere-like, we can apply one of two main formulas, I think, and there are more of course, but the volume of a sphere can be thought of as 2/3, right, of a cylinder of same height and base area. So we think of it as 2/3, right, times pi times radius squared times the height. Now this chunk right here is our cylinder formula, and the sphere is just 2/3 of that. So we can use this volume formula to approach and estimate the volume of the Death Star. So we know that the diameter is 140 kilometers, and the radius, right, is always equal to the diameter divided by 2. It's half diameter. So our radius here is 140 kilometers divided by 2. 140 divided by 2, and that's 70 kilometers. And a sphere is, of course, interesting because in many ways it's like a 3D circle, and that means that the diameter is also the height, right? This diameter right here is the height of your sphere. So in our formula, h is equal to d. It's equal to our diameter, and that equals 140 kilometers. But many of the measurements we're going to use in the future are in meters, and 1 kilometer, right, equals or is proportional to 1,000 meters. So I want to change these measurements to meters. So 70 kilometers becomes 70,000 meters, right? Same distance, different unit. And 140 kilometers becomes what? Well, that would be 140,000 meters. And now we have enough measurements, right, to work with our volume formula. Let's just fix that. So you have 70,000 and 140,000. If we plug that into this formula right here, we'll have 2/3 times pi times our radius squared, which is 70,000 squared, times our height. And if we work that out, we get a number, right? And I don't need to show you those steps here. We can work that out on a calculator. But what I get is approximately, right, we're estimating here, 1.44 times 10, right, to the 15 cubic meters, because we're dealing with the volume here, so we're dealing with space. Now this is an enormous size, right, the volume of this shape. 1.44 times 10 to the 15th, that's in scientific notation. If we rewrite that, what we get is 1, 4, and 4, and then 13 more zeros. 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13. Here is our volume of our Death Star, right, in cubic meters. So this is the size we're dealing with. So before we even go any further, we just need to appreciate that this Death Star is truly enormous. Now the next question we begin to think about is, okay, well that's the volume, but how much material would we need to make this shape, right? Because although this is a sphere and that's the volume, the Death Star is not this enormous spherical ball of steel, right? There are passages inside, there are all kinds of machines inside, there's space inside for people, there's all kinds of things. So the question is, how do we deal with that? Right? How do we take into account all those complicated variables and all those passageways and engines and things that would go inside this sphere, right? Because this is the total space, but how much of it is really filled with stuff and material? And that's where we begin to model this problem, because here, right, we start to estimate with our spherical shape. Well, now we need a way of thinking about the complexities of the inside of this shape without dealing with all the specifics. Okay, so how do we figure out how much material and how much mass will actually be in the Death Star? Well, in the article, what they did, and what I think is really clever, is to use a model of something that we already have built, right? And to say, okay, well, the way this ship right here is built, let's use that to model what the Death Star will be like. Because here is a ship, this is the HMS Illustrious, right? In this ship, the HMS Illustrious, I'll spell it out, we know the mass, and we know the tonnage, and we know the volume of this ship. And we can use that to say, hey, well, inside here are passageways and wires and machines and weapons and all these things built that would model what we would kind of find in the Death Star. So what is the mass of this ship? Well, the mass is about 22,000 tons, right? And the volume is about 28,591 cubic meters. So we know the volume and we know the mass of this ship, and that's our working point. And just to give you a reference, this is a rather large vessel. A mass of 22,000 tons is about 49 million pounds, or about 22 million kilograms. This is a very large vessel. And what we can do is set up a ratio, and it's the ratio of mass to volume in the HMS Illustrious. We're assuming it's somewhat proportional to the Death Star. So we're going to say that the HMS Illustrious has a mass to volume ratio, right? This is of the HMS Illustrious. And then we're going to scale that up to the mass and volume ratio of the Death Star. So we're going from the HMS all the way up to the Death Star. And this is just a matter now of solving a proportion, right? Because we know the mass and volume of the HMS Illustrious, and we just found out the volume of the Death Star. All we're doing now is finding the mass of the Death Star. So the ratio could be something like this. For the HMS Illustrious, we can set it up down here, so it says 22,000 tons, and I'm going to leave it in tons. Right? Tons are a larger measurement than both kilograms or pounds, and thus will give us a smaller number. Right? This tonnage takes into account more weight. So 22,000 tons on the HMS Illustrious for 28,591 cubic meters. And that's going to equal some mass, we'll call it X, of the Death Star over the Death Star's volume, which was that enormous number we got just earlier, right? This Death Star has a volume of 1.44 times 10 to the 15th cubic meter, right? And that's in cubic meters. So now there are many ways to solve proportions. Many people like to cross multiply, but I like to often divide. And what I mean by that is I'm going to find out 28,591. How many times will that go into, right, 1.44 times 10 to the 15th? Right? And what that's telling me, by dividing the size of the Death Star by the mass or the volume of the HMS Illustrious, that tells me how many of these ships right here it would take to equal, right, the volume and size of the Death Star. And then all I have to do is multiply that number by the mass of the ship. So I'll walk you through those steps. So first we take the volume of the Death Star. That's 1.44 times 10 to the 15th, and then we divide that, right, by 28,591. This is all in cubic meters, but I'm not going to write the units in there. And when we divide these two numbers, that will tell us how many times does this ship, the HMS Illustrious, right, need to be repeated to equal the volume of the Death Star. And that's a surprising number. When we divide these two out, we get about 49, right, billion, 627,129,140. That means almost 50 billion of these ships would be needed to be put together to equal the volume of the Death Star. It's quite stunning. And what that says is, okay, well, we know how much each ship weighs, right? Each one of those ships is about 22,000 tons. So now to get our mass of the Death Star over here, right, we can just multiply 22,000 tons times this number right here, because we know that each ship weighs that much. So if we have about 50 billion ships, and each of them weigh 22,000 tons, and that's about what the Death Star is, it's just a matter of multiplying to make the final calculation here. So we're going to multiply 49,627,129,140 times 22,000, right? And that's in tons. So this is going to tell us the approximate tonnage of the Death Star, which is, of course, enormous. 1.09 times 10 to the 15th power in tons. That's about how much material you would need in order to make the Death Star. And this, of course, is a 1 followed by a 0 and a 9 and then 13 more zeros, similar to what we saw earlier. Okay, so I noticed that I'm running a little long on time here, so I'm going to break this video in two parts, and the next one we'll look at how we would actually go about figuring out if the Earth has enough material to make this vessel, and then how much time it would take, and finally how much it would actually cost.